Today, we're digging into something that powers just about everything, from your video games to complex economic models, matrix multiplication. And we're about to find out why its super weird definition is actually its greatest superpower.
Okay, let's just get right into it. If you've ever taken a linear algebra class, you've definitely asked this question. Why can't we just multiply the numbers in the same spots, right? Why this whole complicated dance with rows and columns? It feels so backward. But believe me, there is a very, very powerful reason behind the madness.
So here's our roadmap. We'll start by showing that there are actually two ways to think about this. Then, we'll unpack why that weird way is so important. We'll even look at a new way to see it using blocks, dive into the incredible race to make it all faster, and wrap up with a deep, unsolved mystery at the very heart of computer science.
All right, first things first. Let's clear up something that trips a lot of people up. When someone says matrix multiplication, they could actually be talking about one of two totally different things.
On one side, you've got element-wise multiplication. It's exactly what you think it is. Simple, intuitive. You just multiply the numbers in the same positions. And that's great if you're tracking things that are totally independent of each other. But the one we're really focused on today is the standard method. This one uses a process of combining entire rows with entire columns, a dot product, which is the key to understanding how whole systems of values influence each other.
So that's the big question, right? Why on earth did mathematicians land on this much more complicated row-on-column method as the default? What's the secret sauce here? Okay, so the formal definition sounds a little dense, I know, but the idea behind it is actually pretty straightforward. To get just one single number in your final matrix, you take a whole row from the first one, a whole column from the second, and you mash them together. Let's make that real for a second. Imagine you want to find the value for that very first spot, top left corner of your answer. You grab the entire first row of matrix A, you grab the entire first column of matrix B, you multiply their first numbers together, then their second numbers, and so on. And then you just add all those little products up, and boom! That's your answer for that one single spot.
And here is the absolute key takeaway. This isn't just random arithmetic. This specific process, it's the language of combining actions. If one matrix represents a rotation and another represents a scaling, multiplying them gives you one single new matrix that does both at once. It's how we solve incredibly complex systems of equations and model how things in physics or economics are all interconnected. The weirdness is actually what makes it so powerful.
So now that we kind of get the why, let's look at a more advanced way of thinking about the how. This is a technique that pros use, and it helps reveal these deeper structures hidden inside the matrices.
This idea is captured perfectly by the mathematicians Stefan Ramon Garcia and Roger Horn. They basically say that to really master this stuff, you have to stop seeing matrices as just a grid of numbers. You have to start seeing them as collections of smaller matrices, or blocks. And that's the whole idea of block matrix multiplication. You can literally draw lines through your matrices, breaking them up into smaller chunks. Then you can apply the same multiplication rule we just talked about, but you treat those blocks like they were single numbers. It's the exact same calculation, just organized differently. And thinking this way, well, it can lead to some really elegant proofs and amazing new insights. All right, so because this operation is so fundamental to, well, everything in modern computing, it has sparked a decades-long question in computer science. Just how fast can we possibly do it? Let's look at this incredible journey. The method you learn in school, the standard one, takes roughly n-cubed operations. That means if you double the size of your matrix, it takes 8 times as long to compute. That's a huge penalty. But then, in 1969, a guy named Volker Strassen came up with a mind-bendingly clever way to do it faster, with a complexity of about n to the power of 2.8. And ever since, researchers have been in this intense race, just chipping away at that exponent, getting closer and closer to the theoretical limit.
And this race, it's had these long periods of total silence, followed by sudden, shocking breakthroughs. Strassen's discovery came out of nowhere. Then the Coppersmith-Winograd algorithm in 1990 set a record that nobody could beat for 20 years. The pace has picked up again recently, with the latest record just this year, in 2024, pushing that boundary just a tiny bit further.
This whole quest brings us to one of the biggest open questions in all of theoretical computer science, the hunt for a fundamental constant of the universe, known as omega.
So omega, that's the symbol for the true, ultimate exponent from matrix multiplication. It's like a cosmic speed limit. It represents the absolute fastest this operation could ever possibly be done, even in theory. We don't know what it is, but we've been hunting it down for decades. And this is the grand prize, the holy grail. Is omega actually equal to 2? Could we multiply matrices in n² time? That's as fast as it takes to just read the numbers in the first place. Most experts think the answer is yes, but no one has been able to prove it. Finding an algorithm that does that would be a world-changing breakthrough.
But, and this is my favorite part of the story, there's a fascinating catch. As we get closer and closer to that theoretical limit, the algorithms get so complex that they've earned an incredible nickname, galactic algorithms. And here's why. Even though they're theoretically faster for huge matrices, the setup cost, what we call the hidden constant, is astronomical. This means for one of these record-breaking algorithms to actually be faster than the simpler methods, you'd need matrices so ridiculously massive they literally wouldn't fit on all the computers on Earth combined. They are, for now, a beautiful piece of theory.
So this is where we stand today. We know omega has to be at least 2 because you have to look at all the numbers, and we know it's less than the current record of 2.371339. The true answer, that fundamental constant, is trapped in this tiny, tiny sliver of a gap, and it's one of the biggest prizes in modern mathematics.
In the end, this isn't just some abstract game, because matrix multiplication is so central to everything we compute. A breakthrough here, especially a practical one, could massively accelerate progress in AI and physics, in basically every field of science. It really makes you wonder, doesn't it? What amazing discoveries are just sitting there, waiting for us on the other side of this one wonderfully weird puzzle?